We heard various names for our lecturers. Sometimes they're called Professor. I'm going to call them Dave and Kathy. So we heard Dave talk about the second law of thermodynamics and some of the physical origins of the natural processes, which were then amplified by Kathy into the heat engine of the Earth. I'm going to finish off with how humans tap into the various heat sources that the Earth and the Sun provide for us. And I want to, so one progression that we've heard is physical facts, right? So physics, second law of thermodynamics, universe, Big Bang, all the energy that Big Bang is still here. Those are physical facts. Kathy told us about what happened on the Earth geologically and over the 4.5 billion years that the Earth has existed, how it's evolved, where the oxygen came from in the atmosphere, life forms evolved, we started to use energy, so we tamed fire, and we realized that energy could really raise our lifestyles. So since the Industrial Revolution, so 1750, let's call it, we have more and more tapped into the natural energy sources that are around us to make our lives easier and to build a couple of things, one of which is our population, which is now expanding very dramatically. So 7 billion people on Earth now, thought to go to 9 billion. But who knows, those are just estimates. That was enabled to a large extent because we were able to tap into energy other than the 100 watts that each one of us produces and the slightly more than 100 watts that our farm animals, horses, oxen, other animals that we use, what they produce. So by tapping into all this energy, we've really raised our lifestyles. But we've got another thing, and Kathy touched on this. We've started to mess with, it's a good word, the system that produced those things. Some of that messing, we understand, and we can sort of know where it's going to go, and we shouldn't do it. And we've actually, to go back to the 1970s, we cleaned up the atmosphere a lot. I remember the 1970s when I lived in the suburbs. I could look east toward Chicago, and every day of the year it was great. And that's just because the air was polluted over the city. Not true anymore. So we learned a few things, but we're still in that learning cycle. So I want to compare everything. This will be kind of a whirlwind, but you will, from the three of us, will have gotten the basis for the next 2 weeks, which is, let's talk about this energy use. So these are the basics. So I want to talk about the sources. How efficient is it? So Dave told us about the Carnot efficiencies. So where are we on that Carnot efficiency cycle? And what does it cost? So we humans, because economics kind of rules our societies, we like to do the cheapest thing. And if you want to predict in the future, what are we going to do 20, 30 years from now? You ask, well, how much is it likely to cost? So we'll take a look at the relative costs as they are now. And then the last slide will show what we've done over the last 150 years, where we are. And I'll try to project a little bit about where we might go. So let's first look at the big picture. That ring on the right, that's all the energy that the US used in 2013. And the other developing countries are not so different. The two things in color are the big sectors. So electricity grid is the biggest one, 39%, that's a lot. The next biggest one is transportation, that's the gasoline in your tanks of your cars, basically. And then you see the two gray things which are related but not directly related to those two. So that's about 2/3 of our energy. And they're both, we were talking about the future, the past and the future, so we look to the future. They're poised for transformational change. So the big change in cars might be electric cars, and we'll have more to say about that later in the 2 weeks. But the reason we don't have an electric car right now, why everybody doesn't own one, is that the batteries aren't good enough. So you can go maybe 40 miles or 60 miles on a battery, or if you have $100,000, you can buy a Tesla, and you can actually go 250 miles, and that sounds pretty good. But you'd like to get that price tag down to where everybody can afford it. So that's batteries, that's energy storage. And the electricity grid, which is going through a transition. You see it there, coal to gas to wind and solar. So thanks in part to our environmental concerns and to the EPA, which has limited now the carbon emissions of coal plants, we're making a switch. And the conventional wisdom is that in the United States there will never be another coal plant built. Why? Because the economics won't support it. Because these regulations make it so expensive to build a coal plant that doesn't emit as much carbon as the ones we have now, that we just won't build them. So what do? We'll build gas plants. Why gas? Because in the last 5 years, fracking has made gas really cheap and really abundant, and the projection is that's going to persist for the next 10 or 20 years. So that looks like a way better deal than coal. Good for us too, because gas emits about half the carbon that coal does, so that's a step in the right direction. But there's one more thing, and that's wind and solar, and these things don't emit any carbon, basically, except for the infrastructure that you have to build a solar cell or build a wind turbine. So that's an even better deal. So we're in the middle of change, and that's the point. It doesn't seem like it because it goes slowly enough. But in 10 or 20 years, you'll look back and say, oh my God, that's what we did in 2014? So here, as an example, Kathy talked a little bit about fossil fuels. I'm going to talk about electricity. So here's electricity and its history going back to Thomas Edison's day, which was around 1880. And how much of our primary energy, we said it was 39% now, was it over history? And you look at some of the things that electricity does, it really does it's enormously versatile, right? So you can see that picture up there because of electricity. We're powering a projector with it. And I use electricity to change the slide. And here's some other things. Transportation, certainly in the cities. CTA, you'll be taking the blue line probably while you're here. Runs on electricity. And you see some other things there. So it's really pervasive. And the reason we like it so much is that it can do so much for us. Communication, your computers, cell phones, and all that. It just seems to have endless uses. So here's the first way we generate electricity, fossil fuels. You've seen a picture like this, maybe even this very picture, which Dave showed. And harking back to Dave's lecture, think of all the energy conversions that have to happen for this coal plant to work. So you start with chemical energy in the coal, and in come 6 railroad cars of coal an hour. To me, that sounds like a continuous train coming 24 hours a day. And it stops just long enough to unload the coal, and it moves on. It's really quite amazing. But the chemical energy in that coal, it gets burned, so that turns it to heat. That heat evaporates water, that produces steam under pressure. That pressure pushes a turbine, so the steam pressure turns into rotary motion, kinetic energy. That turbine turns a generator, which is just stuck on the end of the shaft that's turning, and that makes electricity, usually from magnets, the rare earth magnets that Kathy was talking about, and that electricity then goes to the transmission lines that comes to us. And we heard that it's about 35% efficient, so in a sense, turn that around, it's 65% inefficient. So 65% of that energy isn't going anywhere useful, actually. Anybody have an idea where it appears? Question?
Yeah, quick clarifying question. Is that 35% relative to the optimal Carlo efficiency,
No.
or is that just, yeah?
Great question. So that's 35% absolute. And as we saw, it could be 60% efficient, about. Yeah. So we're getting about half of what we could. And that's a very important point because the Carnot efficiency is limited. So you can never get 100% of it useful. But we're getting about half of what we could get. And if you compare that to a gas-fired plant, so it's called combined cycle, that means you get one cycle, one turbine turning from the combustion of the natural gas instead of coal, it's gas. But then the exhaust steam from that still has enough heat that you can turn another turbine, a second turbine, so it's a combined cycle. And from those two things, you get, in the best ones, the most modern ones, 60% efficiency. So that's getting really close to the Carnot, your question, getting very close to the Carnot limit. And that means that you can do a lot better than coal. And it turns out that's the highest efficiency pretty much for any kind of electricity generation. And why is it so high? Well, it's high because we've been playing with it for a long time. So we've had 100 years to really make it good, and we understand turbines pretty well. So, there's the Carnot efficiency there. So, all right, that's, now nuclear, Dave showed this as well, something like this. And it turns out it's about the same. You might think it's better, you might think it's different from a fossil fuel plant, and the only thing that's different is where you get the heat from. So instead of burning a fossil fuel, you get it from the fission of uranium nuclei. But you still get a heat source, you still have a steam pump, and as Dave was saying, it's really about the same. So what is the major difference? Well, you're not burning fossil fuel, great. You're not depleting a precious resource, well, you're depleting uranium. And it turns out uranium, the amount of uranium you can easily get from the Earth is several hundred years worth, which is about the same as the amount of coal that you can easily get from the Earth. So there's a trade-off there. You're not producing carbon dioxide. That's the main advantage from our point of view of nuclear. What else? Hydroelectric. So we talked about this earlier too. Doesn't have anything to do with the carbon efficiency because it's not really heat driven. It's just kinetic energy. Rain, we saw the hydrologic cycle, so rain, water is evaporated from the ocean by the sun. It leaves the salt behind, so that desalinates it. It's a way of purifying, making fresh water. It's transported through the atmosphere by atmospheric circulation, condenses over land and falls as rain. What a great way to get fresh water from the ocean desalinated and transported free of charge to the land where it falls as rain. If there's a mountain that it falls on, it falls at the top of the mountain, forms rivers. Those rivers run down the mountain, and that's kinetic energy that you can then use. And so there you see the cycle there. And interestingly enough, at one time in the United States, go back to the 1930s, you might be surprised to know this, that almost all, maybe 75% of our electricity came from hydroelectric. Because back in those days, everyone realized what a good idea. It's free. All I do is build a dam. Now we've kind of reversed our thinking. We're actually taking some dams out because of the ecological damage they do to the ecosystem. But this has kind of, at least in the U.S., run its course. So all the good dam sites are taken, and there's some left, but there's not a lot of room there for expansion. The next thing, solar power. There's two kinds of solar power. This is the first kind. So solar thermal, you take a parabola, so you reflect the sunlight in a parabola, focus it at the center of that trough, and in the center of that trough runs a pipe. It has a liquid, it's usually not water, but it's like water. You heat it up to a high enough temperature where it can run an ordinary engine. So it's just like your car engine, a gasoline engine, except the heat doesn't come from combustion. It comes from just simply focusing the sun's rays and heating water or something else to be the T-hot in the Carnot cycle. And it turns out, so there you see the numbers, 150 degrees C to 350 degrees, that's roughly where it is. It's usually molten salt, not water. And you have vast areas of land. I shouldn't say vast, not vast like the wilderness, but square miles of land covered with these focusing troughs that capture the sun's heat and produce maybe 350 or 400 megawatts of electricity. So in the southwest Mojave Desert, you find these things actually, they date back to to the 1980s, which is before we became so energy conscious. It was simply realized that the sun was bright enough, the cost was cheap enough, and these were installed. And for a long time, those were the only ones. Now there's starting to be a huge range, and I'll show you some data on that. So they run about 30 or 35% efficiency. For a long time, they were the most efficient form of solar power, more efficient than a photovoltaic cell. So that's what you see here. This has no moving parts, really nice in that sense. So you see on the right a little diagram of how it works. There's a semiconductor with electrons in the so-called valence band filled. Then there's a gap, that's really what a semiconductor means, there's a gap. And then the conduction band, and a photon from the sun comes in, and comes in here, boom, 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 excites an electron from the valence band up to the conduction band. It's then mobile, it can move, and if you put a little junction here, that's why these bands shift, so a PN junction often called. So the electrons go one way, this way, the holes go the other way, and that gives you the source for an electric circuit. But no moving parts, it's all electronic. So you may ask, so what's the efficiency? Well, the best efficiency you can buy now, commercially, is about 22%. That means 22% of the solar energy falling on that PV cell is converted to electricity. You can do better in the lab. So if you stack 2 or 3 of these together, you can get 40% efficient, much better. At the moment, too expensive, so nobody does it in practice, but people look to that as for the future. Remember what we said before, a coal-fired power plant, 35% efficient, a combined cycle gas plant, 60% efficient. This is, in a sense, primitive compared to those efficiencies. And it's really a challenge for basic science to figure out how to get that efficiency up and, of course, the cost down. So it's even more competitive with fossil. Here's wind, another big renewable source. Interesting things about, first of all, so how does it work? Up at the top, of course, you've got the blades going around. They don't go around very fast, and that's by design. We've learned over the years that it's more efficient to make them go slow. And then inside that thing at the top is, there's 2 possibilities there. You can put a gearbox there. So you can make that very slowly rotating blade jack up the rotational speed to something you want, like 60 hertz, and produce the electricity at some frequency which we would use, 60 hertz, and then take that electricity down through the wires that go down to the bottom. Or you can have a direct drive turbine, which turns out much more, there's much less wrong with it. So 90% of the problems with wind turbines are the gearbox. Get rid of the gearbox, drive directly at some very low frequency, and at the bottom of the tower, electrically convert that to the 60 hertz that you need to use. So talking about efficiency, interesting, the theoretical best efficiency for any turbine, any single turbine, 59% of the wind kinetic energy can be taken out. Think of it this way, if you took it all out, the wind would be blowing on this side of the turbine, here's the turbine, and there'd be 0 calm wind on the other side. Kind of ridiculous. You could never do that, because it has to blow through the turbine in order to turn it. So you can never get 100%. But it turns out, way back in 1920, Betts figured out that you could get 59%. So that's like the Carnot limit for wind. And what do we actually get? It's somewhere between 35 and 50%. So it's actually pretty good. If you look historically at the sizes of windmills, of wind turbines, so going back only to 1990, not very far back, this is the relative size, right? As time went on, we realized that the bigger you make them, the better it is. First of all, there's some economy of scale, but secondly, you make it higher off the ground, and the wind blows faster the farther you get from the ground. So you want to make them higher and bigger. And now, we're not quite there yet, but on the drawing boards are things that will have 160-meter span on the blade. And for comparison, there's the biggest Airbus airplane, which has a wingspan of about 80 meters, so way bigger than an airplane. Sometimes you don't notice this kind of scale when the windmills are so far away. So what about our resources? Well, if you take a look at the United States, here is the solar insolation, as it's called, how much energy is in the sun's rays. And remarkably, it varies by only a factor of 2 over the entire United States. We sometimes forget how big the United States is. It's really huge. So it only varies by a factor of 2. That's not much. Of course, it's best in the desert there in the southwest. It's kind of bad in Seattle, Washington, because it rains all the time there. It's cloudy. But that difference is about a factor of 2. Compare that with Spain, always thought to be a wonderful country for sun and for solar, and it is. We're about as good, but a lot bigger. Compare us to Germany. It's a leader in solar energy because they decided they need to get off fossil and they have energy security challenges. So that's the same, on the same scale, that's Germany. We got a lot. And in fact, if you do the numbers, way more solar energy falls on the United States than we would ever need to convert to electricity. So we're blessed in that sense. Here's the wind. It's mostly in the center of the country. That has to do with atmospheric circulation. The fact that the Rocky Mountains are here, right? And that affects how the winds blow, and that means that's where they should be. Take a look at our neighboring state of Iowa here. It's got a lot of wind energy. And you may know this or not, it now gets 25% of its electricity from wind. The state has realized its resource, they've incentivized it, they've made it happen. Here's where we are, Illinois. Actually, Illinois gets a fair amount, but it doesn't have the potential that Iowa has. There's lots more wind on the 2 coasts. Why? Because wind usually blows in off the sea. The ocean's colder than the land, well, during half the day and at night and day and so on. But the wind is stronger offshore, about a factor of 2 stronger, and about a factor of 2 steadier. So these are great places for wind. There's a problem though. The 2 coasts are not the same. So this has to do with what Kathy was telling us, that the Atlantic coast tends to be more shallow. And that means that you can place wind turbines and anchor them on the bottom farther away from the coastline, so out of sight, than you can on the Pacific coast. And so, although there's almost no offshore wind development yet in the United States, a little bit, this is where it's going to happen, and it's not going to happen very much on the Pacific coast. It's just too steep. So interesting. Now, if you look on this map, here's Lake Michigan, and indeed, that's a pretty good coastline too. And it is actually a wonderful resource for offshore wind. And the city of Evanston, just north of Chicago, has for several years had a program, not done yet, to tap into offshore wind on Lake Michigan and feed the city of Evanston a large fraction of its electricity from that source. I don't think I want to spend much time on this, but you can look at it in more detail if you want. It just documents how much wind and solar there is. And let's look at some bottom lines. In the Southwest, so these are just a few states, there's the potential, here's gigawatts resource potential. You see something like, call it 7,000 gigawatts. If you look at the roof area of the United States, all the houses and everything, of course nobody knows what that is, but it might be about 6 billion square meters. That has the potential for 600 gigawatts. If you look at all the land covered by cities, the urban footprint, so that's about 3% of the land, the solar energy, that has the potential for about 2,300 gigawatts. Now, how much do we use of all that potential? In 2009, our electricity use was about 450 gigawatts if you average it over all the seasons, day and night. So if you used it continuously, you'd have to generate 450. The peak summertime is about twice that, so 1,000 gigawatts. So there's plenty. We can actually get all the electricity we need from wind and solar if we were willing to pay for it. So how are we doing? Here's a map of the United States, and you may know that some states, including Illinois, have passed laws that say by a certain date you have to have a certain fraction of your electricity coming from, basically it's wind and solar. Hydro is discounted in these laws usually. RPS, so Renewable Portfolio Standards. So it's actually 30 states and the District of Columbia. The most aggressive ones, California, you might expect. So they say 33% by 2020. And maybe a little bit surprisingly, New York, but New York State is very sort of forward-looking in energy. It's a leader, not quite like California, but maybe the second. So they say 30% by 2015. Here's what we've done. So go back to 1980, there was almost nothing. I was saying earlier about these thermal solar plants where you focus the sun's rays. That's this little bit here. So back in the 1980s, these were built in the Mojave Desert. And pretty much they were built and they've operated continuously but not grown. And then around 2000 or so, we started to grow. I'm sorry, I'm pointing to the wrong thing. This is the solar, this is the wind. So this little tiny thing down here, that's the solar plants in the Mojave Desert. Here's the wind plants, also going back pretty far, but pretty stagnant. Around 2000, everything started to take off. Wind, because it's cheaper, took off faster, and you see it looks like a huge rise, and it's really strong. It's about, both wind and solar grow at somewhere between 30 and 40% a year. It's really quite remarkable. Wind more than solar. The price of solar, we'll see on the next slide I think it is, has really dropped in the last even 2 years, but certainly 5 years, and it's expected that this is going to take off and start to close the gap between solar and wind. So how much is this? Well, this is 60 gigawatts. And we said you have to produce 450 if you did it on the average constantly. So, and you have to remember that 60 gigawatts, that means installed. If the wind blew all the time, it could produce 60 gigawatts, but the wind doesn't blow all the time. So there's a thing called the capacity factor. That's usually for wind 15%. So you actually only get 15% of its full capacity if it were running all the time. For solar, it's a little higher. And so you take that into account. Then we get about 4% right now of our electricity from wind and solar. If I were giving this talk 2 years ago, I would have said 2%. It's really growing fast, but still a tiny percentage. So if you project these 30 and 40% growth rates, and of course it's going to be hard to maintain that as you get more and more, but if you did just for fun, then by 2030 we would be getting 40% of our electricity from wind and solar. So we're kind of in a sense on target. It's imaginable that you could reach these 20% requirements that many states have already passed. Here's the cost. So every year the US government, the so-called EIA, the energy, I can't even remember what it's, you see we all use acronyms so much. Anyway, the EIA, they project what would it cost 5 years from today for every kind of electricity production without incentives. So this is kind of a valuable thing. So the last one they did was for 2018, so 5 years from 2013. And here you see, here's the coal things, various kinds of coal. It's pretty cheap. So this would be, I guess, 10 cents a kilowatt hour, $100 per megawatt hour. And here comes gas, pretty cheap. Here's the combined cycle one, conventional combined cycle, that's this one. Advanced combined cycle, with a little bit better. And that's the cheapest thing on this chart. And that's going to stay pretty cheap because shale gas is going to stay pretty cheap and pretty abundant for a long time. So from an economic point of view, you would say that's the thing to do in 2018. But look at the others. Here's some other gas technologies. Here's geothermal, we didn't really talk about. It's not so far out of sight. Biomass, burn trees. Here's hydro, and it depends a lot where the hydro plant is. As we said, this is pretty much done. Here's wind. It's not so bad, right? So its lower end really competes with gas. And that's one reason why wind has taken off. This has been kind of historical. It's been here. Here's the solar things. Sorry, offshore wind, we should talk about that. Costs about twice as much as onshore because you've got to build it in the water, you've got to anchor it to something. It's really hard to get to it if you have to fix it. The maintenance is expensive. And the salt air is actually corrosive. So North Sea has done a lot more offshore than we have. They found in their earliest plants, after 18 months, they had to replace the hub at the top of the tower because it had simply corroded from the salt air. Didn't expect that. But anyway, about a factor of 2. Whoops. And here's solar PV. So I was talking, the price went down. When EIA did this in they projected 2016, that would have been back in 2011. This was the range for the cost. And the cost has fallen to here. So it's almost a factor of 2 just in a couple of years. It's really amazing. And here's the solar thermal that I was talking about. So this normally governs what we do. The thing that's the cheapest, that's what everybody wants to do. But there is something else, which I'll get to on this slide, it's my last slide. Where are we now? So this takes, and by the way, it's from an article that Steve Chu, the former Secretary of Energy, wrote a couple of years ago. 1850 up to about now. Where did we get our energy from? So it was all wood, and remember that's what Vaclav Smil said. 1850 we were a wood-burning society in the U.S. Then we got to coal, not bad, expanded dramatically, kind of shrunk here recently. And the main thing that coal is used for now is power plants. That's probably going to change. So this, you could expect in the future, this is going to go down. Here's oil, from which we actually don't get any electricity. This is total energy. That's transportation, so that's what you have in the tank of your car. Here's natural gas, so growing. It's probably going to grow more because shale gas is so cheap and abundant. Here's the renewables. I'm sorry, here's the nuclear. That's what this yellow is. And it experienced really rapid growth back in the 60s, and then suddenly, for reasons we can all understand, since 3 Mile Island in the late 70s, since Chernobyl, middle 80s, and since Fukushima, 2011, everybody is saying, it's mainly driven by the public, is this safe? Do we really want this? Is this how we want to spend our, obtain our energy? And a really fascinating story, but that's for another time, about what might happen to nuclear. And then you might say, well, how about wind and solar? Well, there they are. You can almost see them, but that's what they are. It's just that small. So this is where we are now. Where are we going to go in the future? So I was talking about economics. It depends on the cost. But all of the projections that you make for the next 20 years or 30 years typically leave out one of the most important things, and that's discovery. So things that don't exist in our imagination or on our radar screen now, but will be discovered. And I'll take you back only either 5 years or 10 years before we said the word fracking. And that changed, it was a game changer. So since about the last 3 years, maybe 4 years, we've understood what fracking means. Nobody did it 10 years ago to any significant extent. Nobody thought it would be big. It confounded all the predictors, and now it's in our equation, but it's changed the way we think and the way we do business. Well, there are other things out there. So that was mainly an engineering development, huge innovation. But there's lots of scientific discoveries we can do. And one of the lectures we'll have next week, we'll look at that a little bit more carefully. So I think that's it. We're done. I'm going to leave you with that. Plenty of time for questions. And I'm going to ask Thomas, who is now standing up, to tell us what to do next. But this basically is the first tutorial. We'll be around, we lecturers, if you want to talk to us, and it won't be long until we have lunch. Thomas, will you rescue me here, please?